Okay, so thank you very much for of you who got up early enough to be here this early hour, and to the organizers to give me this opportunity. I actually think it's after 2 years, it's the first time that I am for such a long time before a room of audience. So yes, and it is the last time I am as paid by a scientific institution, because in a week I will be officially retired. So I will get retirement cash, or how you call it. This is a joint work with Marco Cavaduro, who is a PhD student, and I am officially one of his advisors, but he's advising me at least as much as I'm advising him. So what I would like to show today is the fun we had with this problem of packing and covering squares. So let's first some terminology. We have some geometric objects, most of the time squares, and we say that a point hits a square if it is contained in it. And the square at the same time covers the point. If you have a set of a family of sets, then a hitting set is a set of points which hits all the sets. And tau is the minimum size of a hitting set, nu is the maximum size of a pairwise disjoint subfamily of sets. Then we have, as usually, nu is at most tau, and what we are looking for is to upper bound tau. This is mainly the main goal, to upper bound tau with a function of nu, which exists sometimes and doesn't exist some other times. So for instance, if you have unit squares, the simplest case, then we do know that tau is at most 2 nu. We will see it in a minute, and cannot give a better upper bound than 3/2 nu. The far goal of this subject is a conjecture of Wegener, which says that for a set of rectangles in general, you can bound the minimum hitting set tau by 2 nu minus 1. This is the bound. There are not really tight examples for bigger sizes. We'll also speak about that. On the other hand, there are approximation algorithms. So the best bound actually is not a constant bound. There's no constant bound for this conjecture of Wegener. The best bound has approximation ratio log nu square. And there is an approximation algorithm according to completely different principles, 2 plus epsilon approximation, which doesn't say anything about this integrality gap. So the integrality gap, the conjecture of the integrality gap is better than this best approximation ratio. Okay. Yes? Interrupt, please. As much as you can. There is plenty of time, as the chairman said.
That's from axis probably the rectangle stuff plus the different sizes.
Yes. Yes. Yeah, if they are the same size, they are like squares, because you can just modify them. So right. They don't even need to be axis parallel. Well, there are other quantities you can define for squares: alpha, theta, chi, omega. So chi, for instance, is the chromatic number, minimum size of the partition of the objects you have into pairwise disjoint sets. Omega, the maximum clique. Omega is not always the maximum degree, so the maximum number of objects that a vertex can contain. There is equality if you have the Helly property, which is not always the case. As you see squares, which are not axis parallel, and they will be our main heroes. These squares, which are not axis parallel, you can have a clique of size 3 without having a point which is contained in 3 of them. Okay, so let's make just a little detour to general gap problems. If you fix an object like squares, this chromatic number, or omega or delta, will have different meanings in tau nu. But at a general level, if you're at an abstract level, maybe chi and omega will be transformed for squares to tau and nu. So there's not so much difference. So studying in a hypergraph the gap between chi and omega says something about tau and nu for squares, right? Because tau is, for instance, for axis parallel squares where you have the Helly property, is the partition, minimum partition into cliques. These points determine cliques and you partition into cliques, so it's the chromatic number of the complement. So when you study the gap in a hypergraph, you actually say something about tau and nu of squares. And András has a paper from the 80s about problems from the world surrounding perfect graphs, which was published in a Polish journal, where he asked many interesting questions and which become actually quite popular these days, also by graph theorists. Actually, many other, not only those which occur in Arbitrary paper, many problems in extremely combinatorics are about gaps. But in Arbitrary papers, Arbitrary's paper is particularly rich in conjectures and ideas about the gap. Recently, let me just mention this papers of Scott and Seymour and then of Chudnovsky, and some of them. Spirkel is a co-author about gaps for graphs which don't contain some odd holes, or odd holes or big holes. And actually they concern a little bit rectangles because they can't contain big anti-holes, so the complement doesn't contain big holes. Unfortunately, their bounds are too big to be helpful, and even when you need a constant bound, they are not good enough because they can contain C5. So it's not true what I said, that the rectangle intersection graphs, or an intersection graph is a graph where the vertices are your objects and you join two if they intersect. They can contain C5, but not bigger holes. So they don't have bigger holes, the rectangle graph. And the results so far didn't give new results for rectangles, although Chudnovsky, Spirkel, and somebody else, a third girl, I forgot the name, directly studied Weber's conjecture when you have only corner intersections. Anyway, there's another paper. So we studied this nearly perfect graphs about which I stated the problem yesterday, but another paper was more useful for us here. It is a paper of Yarfash, myself, and Nicolas Trottignon, which is about the maximum gap you can reach on graphs with n vertices. And we actually determined this number as a function of the Ramsey number as the 3 something Ramsey number. So the maximum size of a graph which doesn't contain a triangle and given clique and cliques are given size. So for instance, here's a Ramsey graph R35. Just you have the chords which are between these vertices of distance 6 and the cycle. So this graph is an example when you first reach the gap 3 between chi and omega. Yes?
So I'm a bit confused. You're talking about any class of graph? Or, I mean,
Any graph.
you're not talking about
No.
axis parallels?
No, not axis parallel, but for the first cases, we needed some computer experiments that people had. So these results of the gaps in general for small numbers were good.
So when you say
this
that-
is 3, yeah, here
So
you
when
have
you say-
a gap of 3, actually in the complement, the size, yeah, actually you will see it in a minute. Oh no.
So, and when you say it increases
I
by
didn't.
one,
I put it there. It increases by 1, the gap may increase by 1. So there is a graph with a gap. So for 5, it is the first number for which there is a graph with gap 1, the C5. Smaller graphs are all perfect.
I see.
Then 10 is, actually it's 2 disjoint. So actually when we started the problem, we were a bit naive. We thought maybe it is just disjoint copies of C5, and then we realized that Ramsey graphs, so on 13 vertices and then on 16 give one bigger gap. So these are the, and actually, yeah, so extremely combinator visions like to make approximate estimates log n, log n, log n over log n. But we could avoid this by just using Ramsey numbers as a black box, and places where this gap increases are exactly with the Ramsey numbers, maybe 1 or 2 or 3 less or more, but they are just with a very small additive constant, the Ramsey numbers of triangle free graph, so R3 and something. But we didn't prove this conjecture that I don't know why it's missing, that the extreme cases are always for omega equal 2. And this might be the case also for squares. So omega equal 2 is important. And the intuition behind is that if omega is equal to, then, so if there are no triangles, then the triangle covering number will be high. And so the clique covering number will be relatively high and will have a big difference with alpha. So here, this is the case. This is theta minus alpha, which is becoming 3 with this graph. Anyway, it's just to give an intuition and to say that it does say something, at least for small numbers, and better than we or others would do with computer experiments. Okay, now hitting and cover, we go to our main task, hitting and covering unique squares. So first, axis parallel squares. For most of the simplest results, there is a nice 2-page note of Alsvede and Karapetyan of statements without proofs. And that's what we started with Marco. And most of these statements could be proved. Some of them were really easy. So the axis parallel cases in particular, very easy. But okay, I am not yet stating the results. I am stating a reformulation that will play a major role for us, the equivalence of hitting and covering. But hitting and covering is almost the same thing in our mind. Both are set covering problems. You cover something in both, but you cover different things. So at the hypergraph level, they are both covering problems. But for squares, if you're hitting squares or covering by squares, it's not the same thing. On the other hand, for unit squares, it is, you have an equivalent reformulation of hitting to covering. Why? Because if a set of squares, and this doesn't depend on the Helly property, this also holds for this. If you have a set of squares which have a common point, set of unit squares which have a common point, that means that the centers of those squares can be covered by a square of that common point. So here it is. Here is a square around the common point. And of course, if this is a common point, this means, yes?
In any move this window on the top somewhere else, or somebody.
Well, that's only upper authority scan. Oh, okay. Okay. Yes, so this is a common point. This is a distance 1 in both directions, so in L infinite norm from all these points, and that means that a square with that center will contain all the centers. So it is equivalent. So the set of axis parallel unit squares has a common point if and only if their centers can be covered by an axis parallel unit square. So there exists a point, a distance L, infinite norm distance at most 1 from all. This is equivalent, and we have the same for
1/2.
Pardon? No.
No, so unit side or
Yeah, 1/2. The L
Yeah.
infinite distance is half, 1/2, right? Right. Within a unit square. Okay, yes, and unit disks also have this property. They don't have the Halley property. They may very well intersect, not all intersect, but this property still holds, of course, for the same reason, with the same proof. So I don't even.
It's a different norm. That's it.
It's a different norm. It's the L2 norm, and you can take any norm, and people did take other norms. So you choose another norm, and we learned at school that norm can be defined with its unit ball, and which is a central symmetric body in arbitrary dimensions, and so you get what we just said in arbitrary dimension, but we won't deal with that. But what is interesting is and first we didn't measure the difficulty of this, is to look at the nu equal 1 case. What if objects pairwise intersect? Well, for axis parallel, we have the Halley property. So then tau is 1, nu is 1. There is no difficulty, but already for disks, there are results from 2020 still showing an algorithm that when nu is 1, then tau is 4. So there was a non-algorithmic proof before, and now they did an algorithm in 2020. So it's not really an easy problem for disks to find that if nu equal 1, then tau equal 4. Geometers were still working on it a year ago, and they are probably still working on it. On the other hand, for translates of centrally symmetric objects, which contain only axis parallel squares, because it has to be the same object and you translate it. But in general, Grünbaum showed long ago, in the 50s, that if nu is equal to 1, then tau is equal to 3. Tau is at most 3, and there can be equality, and then it turned out to be true also for not necessarily centrally symmetric bodies in 2000 Karasev proved. Now, what about dancing ones? That's how we call general. It's just general squares, which don't need to be axis parallel. Well, you can't have this reformulation, but you have something which is so you have two directions which are a bit weaker than the reformulation. So if you have a set of unit squares with a common point, then the centers can be covered by a disk of size square root 2/2. Right? Because that's the biggest distance that you can have in a square. So even if you rotate, all the centers will be at this distance, and then then you can cover by this of this size if they have a common point. And in the other direction, you need to be a bit more strict. It's 1/2. It's the circle. I made a drawing. Yes. So you have the inner circle of size of the radius 1/2, and that's what you need for unit squares to be a common point. But then you have, because it's fully contained in your square. So if you have this stronger condition, then your unit squares will have a common point. So this gap will allow to reformulate hitting problems into covering problems, again with a little weaker results then.
So in Grundbaum and so on, all of these are convex bodies, right?
Right. I didn't try this.
Well, you kind of.
Yeah, central symmetric convex, right? It's not written in the yellow reminder.
And when you say,
Above it's written there. Yeah, they need to be convex anyway. Yes.
and when you say Helly property, you mean that if any two intersect, then all intersect? Or two, of course, if any three intersect, then all of them.
Yes, yes. I mean, if any two intersect, then all intersect. We are in 2 dimensions, and that's yeah. In general, in arbitrary dimensions, any k intersect and all intersect.
Dimension plus 1.
Well, it depends. So in 2 dimensions, it is 2. So anyway, what I mean here, it's very simple, is that pleats are, if you have an omega pleat, then you have a point.
Yes.
So that's
So you just want to say about the intersection.
yes, I don't want to say more.
Yeah.
Okay, so let's go to what we to see our goal after this warming up. Oh, it's okay, we are in time.
I might translate.
Fun?
I have the translate next to me.
Oh, so I'm completely they've unveiled. That was my first, when I started to prepare the slides. That's what I wrote to myself. But I don't know how it could remain there. But it's not to be translated. There's nothing interesting there. So this is the. So we have it. It's about empty tables. So we have our example of C5, which already occurs for axis parallel unit squares. You have nu equal to tau equal 3. And Marco had a nice example for dancing squares, where you need, if you just have this triangle, you can still hit with 2 points. So you need to do something more to get 3 points, this green one, and do it symmetrically for all the 3 squares, and in this way you have 3. You should have 9 squares, because you do it in 2 different ways, right? For each, and you have tau equal 3. So the bounds that you have for axis parallel are at least for the supremum of tau over nu is at least 3/2, and at most 2 for squares of equal size, and for squares of arbitrary size, you have between 3/2 and 4. We don't have a better lower bound. That's why I put it in red. It's a shame that there is no better lower bound. There is no better example for lower bounds. These 2 bounds occur in this paper of Alsvede and Karapetian. I will tell the proofs are very simple. For arbitrary squares, there was nothing except some general bounds on convex bodies, which are very high. And this is the ideas that stimulated some interesting observations about the geometric problem. This is what I will speak a bit more. This arbitrary case and the upper bounds 6 and 10.
So,
Yes.
if you have convex, the same convex set, and you ask the same question, but for a fixed convex set, so that same as the equal size case, do you also get a constant bound in general?
No, not if you rotate also. If you
Okay,
rotate,
you
can take lines, just lines, which have pairwise, every point is contained in at most 2 of them, but tau is as much as the number of lines you have. So there is no 4 lines. You need some fatness assumption. So
But if it's just translates.
pardon? But for just translates, you do have constant bounds. But that contains only axis parallel case,
Yes.
which is very easy for us. So
Yes. Okay.
please, other questions? I will finish too early then if you don't have questions. Okay, so we think we are quite happy with the upper bounds there, but the lower bounds are missing some effort. Okay, so the complexity is quite boring because there is a p-task for all these cases. Partly answers, even if you rotate. So there is a p-task for all these, which have quite high complexity, but they are p-tasks. And on the other hand, the motivation is still algorithmic also, because for Wegener's conjecture, as we saw, the bound 2 is better than the approximation ratio. So understanding the approximation ratio, and you start with simpler cases like squares, it goes towards a better understanding, and maybe getting this ratio of 2 with a nice algorithm, taking into account the ratio of a new ratio.
The approximation factor is below 2 for axis parallel
Rectangles.
rectangles.
The approximation ratio is 2 plus epsilon.
No. I can tell you, it's below 2 now. Yes.
Oh, it's below 2.
Yes. Yes.
Well, we have.
There could be a bilance, but it's still now it's below 2.
And this is just recent result of yesterday, or?
No, it's 2-3 years ago.
In the last papers I saw some people.
No. Yeah, no. Sorry, I'm confused with that. No, you're right. No, you're right. It's
Yes, András.
Yeah.
Your names were.
What you just mentioned before.
Pardon?
Yeah.
It's 2 plus epsilon, right?
And what then we have.
And it's only for tau, so only for nu maybe, and not for tau, for one of the 2. And it's a bit frustrating that you have for one and not the other. So I must question. Pardon? You have for the independent set and not for tau.
Yeah, how is it the hitting set number, right?
Pardon?
How is for the hitting set, right?
Yes.
Yeah, this I don't know.
Yes. Okay. So that's also a challenge to have the same for the hitting set 1/2 ratio, and the nice proof would be to have Wegener at the same time and the common proof for the 2. Yes.
It's about so it was really boring, the complexity, because it's a fast or efficient task for some of these problems. Or
So you contest that it's boring.
no, what is wrong? So all this process, this it's a task for this object. But is it possible to obtain efficient task?
So the dependence on epsilon is not in the epsilon.
Because Ferrari time on this algorithm.
You mean FP task?
No. It's like f of epsilon times the polynomial is independent from epsilon, but f of epsilon can be
Right.
as much.
Right. So I guess this is the case, but this is not the goal of my talk. So I don't know very well, but here there are experts of this.
Okay.
But I think they are exponential, right? The functions.
Okay,
This problem is W1 hard, so unless APT equals W1, you're not gonna get an integer that you.
Even for the squares, we can correct it.
Irregular squares.
Okay, yeah, thanks.
Okay, so it depends hardly on the difficult way from epsilon. Okay, so let's go to work. Let's see this simple proof for squares of equal size. So if the squares are of equal size, we take the leftmost one. And all the others which intersect it will intersect the two right corners, right? Because it is the leftmost one. So if you delete and you delete all the neighbors, then you can do induction, and this induction gives you the tau at most 2 bound, right? Because tau decreases by at most 2 and nu decreases by at least 1. If you delete this, you do induction, you add back what you had, and you have your bound. Okay, and the phi half from below comes from C5. Now, what if you have arbitrary size? You can also take the leftmost. Then you can take the leftmost, the one which has the leftmost center, or the leftmost right, or leftmost less than. For intervals, we know this nice minimax theorem of Golay, which has a simple proof that you have to take the one which has the leftmost right endpoint. That would be good. But whatever you take, if the squares are of different size, you might have many which intersect your square. So this will not be good. But if you take the smallest of the squares, that will be good, because that will, all those which intersect it will intersect it in one of the corners. So you get with the same argument, tau is at most 4 nu. Karapetyan, Alsved and Karapetyan, I don't know why Alsved is named. That's the same 2-page note where the result just occurred. Okay, what about densing ones now, about which we seem to have the first results? Well, you can also take the leftmost one, but they might be many. And tau may also be, we will see examples where tau is also high for the neighbors. But indeed, it's a bit boring too that you have all proofs for this tau nu bound are about bounding the neighbors. So the issue is not to change this, because when you try, actually some of the lemmas that we will see, some of the statements will be not only about neighbors, but the bounds are worse. So these give the best bounds, but the challenge, the most new ideas come from estimating this number of neighbors for equal size and for not equal size, arbitrary size rectangles. As well, then you take the smallest one, but you may have many again, but they can be estimated. This number can be estimated, and this is quite interesting, and the major problem of this problem, to estimate the number of neighbors you can have. And it is related with this covering number that we had. Let's see. So what is the difference between, yes?
To be clear, for the smallest one, most to the left or something, you want to see how many points you need to cover all of the neighbors.
Right.
That's what you want.
Right. Tau of the neighbors. Tau of the neighbors is a problem that we all analyze in more details.
Yes.
Tau of the neighbors, and already we get some intuition that if you have equal size, you will have only neighbors in one half plane. The centers will be in one half plane because you can take the leftmost one. Yeah, it's not very useful to take the leftmost one if you have arbitrary size. So you will have to look at all the neighbors all around. So we will see more examples of this. So, and already now, so what is the difference between unit and arbitrary size for the hitting set of the neighbors? So it's not the size which is the difference. And this is the first remark, which comes from old papers. There are signs already, informal signs in some old papers of Post, but it occurs more explicitly in a paper of Kim, Gostochka, and Nakprasit, that if you look at the neighbors of a square, say, or well, they have more general convex objects. So they have general convex object. They have the neighbors. For them, it translates of a convex set, and which intersect. So these are, that's why they are neighbors, because they intersect it. Then you can apply a homotopy. So if you take the smallest one, then you can apply a homotopy, the central homotopy from the intersection points, and that only decreases tau. So you make a central homotopy which makes all squares of the same size. If you have the smallest one, then the homotopy will only decrease the sizes. So the tau will only increase, and the upper bound you will get for tau will be valid for the original problem as well. And you may have equal sizes too, so you didn't make anything bad. So you can actually suppose that all neighbors are unit squares, even if they are not unit squares. The only thing that changes that you took the smallest one, and you can have neighbors all around the place. On the other hand, if you had unit squares in the beginning, you take the leftmost one, and you will have only centers on a half plane. So the difference between unit and not unit is not the size, but the set of neighbors have to be considered on a half plane or all around in one case and the other, respectively.
Did you say you scale down towards the center of the
no, not of the center of the green one. So the green one is the one whose neighbors we are looking for.
Yeah.
And the centers of these homotopes are different for each of these squares of different size, and they are one of the intersection points.
Any one of these.
Anyone.
Oh, right, because they only get one. I see. Yes, yes.
Yeah, you can feel it, and actually they have a precise proof for convex sets, so it's
Yes.
yeah. Okay. So again, the difference between unit and arbitrary, that for unit we have neighbors on a half plane, and for arbitrary neighbors in all directions. Okay, now let's go back to covering. So what our task is, as you remember, we had the square root 2 over 2 and 1/2. So we have to, now it became red, the square whose neighbors we want to cover. So we have this red square, and we are looking at its neighbors where do we have to look at its neighbors? Where square root 2 in a neighborhood of square root 2 over 2, right? All the centers of the neighbors will be in this blue region, which is a distance, but the colors are not coming out.
That's better.
Oh, yeah. Yeah, you can see that. Yes, there are colors. So it's in a blue region of size square root 2 over 2. Or did the colors go away or no? Okay, so square root 2 over 2, and we have to cover it because we reformulated our problem in this way with disks of radius 1/2. But if you do this, you can see this done approximately on this figure. And well, you can almost cover it by 6, but there are some gaps, and this is what I would like to emphasize. One of the main goals of my talk, how to get rid of these gaps, which might be useful. More generally, it might be something essential in the way you look at these packing covering problems. That these gaps that I'm not tall enough to show, for instance, here is one, are not so essential, because if you try to put a center there, well, here we will see better examples to that. You will not hit the square. So they are not essential. You can use other things to cover it. It's a kind of geometric rounding. You can forget, you can for free put patches on some of these gaps. But first, let us forget about what is written there. We will not speak about that. Some examples. So you see here an example that the tau of a neighbor, of the neighbors, can be 7, and on 1/2 space it can be 5, and little computation shows that you can really realize this. So for unit squares, not for tau, not for the tau nu ratio, but for the number of neighbors of the leftmost unit square, you can have 5 disjoint neighbors. So then tau is at least 5, and we will prove 6. So in these terms, the lower and upper bounds are quite close in terms of the tau of the number of neighbors. Okay, let's see one patching in details, because we have plenty of time, because that's simple and shows that there's something, and there are 3. We know 3 ways of doing patchings, and they were enough for our bounds, and they improved considerably our initial bounds that we had. So here it is. We have 3 points. This is at most 1, so here we have exactly 1. We have an equilateral triangle, and what I claim is that if you have if you have a center, if you have a square whose center is in this triangle, then it will contain one of these points. Although, if you do this covering equivalence, yeah, you can put disks of size 1/2 around these points, and there will be a gap. So this is the look there. Not here, because here you don't see. You see here as well. So in the middle, there is a big part which is not covered by these disks. So if you just rely on covering, you need 4 disks of size 1/2 in order to cover this triangle, right? So your bound would be 4. On the other hand, if you try to draw squares, unit squares, in this, they will contain one of the vertices of this triangle. But it's not covered. So why is that? Well, it is true that if you have 3 points, a distance at most 1, then any unit square with a center in their convex hull contains one of the points, and the proof is very simple. I didn't write it down, but I can tell, and you can do it. It's if you have the center inside and your square doesn't contain any of the points, then each side of your square will hit 2 sides of the triangle. In particular, 2 parallel sides will also hit 2 sides of the triangle, but the triangle has only 3 sides, so there will be a common side of 2 parallel sides of the square. And if two parallel sides of the square have a common side, then you will need a side of size 1 be hit by two parallel sides whose distance is 1, which is impossible. So your square is obliged to contain one of the. So you somehow used the form also of a square. Not only that it contains, it's a little bit more refined, and it allows to patch, to round, to add the middle of these points, and this allows immediately. This has an immediate consequence. If you have a polygon of size at most 1, then the unit whose vertices are on the unit square like this. It is a 7-gon, regular 7-gon. Then any unit square with center inside contains either the center or a vertex of your 7-gon, right? So because then you can subdivide into your triangles and you can apply the lemma. It will contain one of the vertices, so you will have either the vertices or the center of the 7-gon. And there is a square indeed it contains. So it allows you to patch the whole inside of your 7-gon. Your covering by discs will not cover everything, and actually we tried first to cover in a nice way, but then it's all of a sudden allowed us to forget about the missing parts of this covering by this, and to patch at once all the inside of a polygon. Okay, now the outside, because we also need to patch the outside, sometimes we have to cover neighborhood of square root 2 over 2. So what to do with the outside? They're also using Thales's theorem. So secondary school geometry, we know that some places will never reach your square whose neighborhood you are discovering now. So we have that. So we have this unit square inside a polygon, and if for simplicity, let's suppose that for all sides you have the distance of the middle point of your side. It's too high, but maybe I have a laser. Yes. So the middle point of your Thales disk, so the disk with diameter your side, is a distance bigger from the target square than half of the side. Then you know that any square which has a center outside will never touch this inside square, because since its center is outside, if it doesn't contain one of the vertices, then the intersection with the polygon will be rectangle, triangle, rectangle, or I don't know how it's called. And so by Thales's theorem, the hypotenuse of this rectangle triangle will be inside a side of your polygon. So it will not hit. It's just a distance criterion for not hitting, and so you can patch that point even if it's not covered by disk that initially we wanted to cover with, but the disk of radius 1/2 around vertex of the polygon. And in fact, you can do a bit more. You can even have this distance criterion violated because there is a triangle which has to satisfy the triangle inequality, and by this triangle inequality, you get that even if this distance criterion doesn't hold, sometimes you can patch. So there are these three criterions, and now let me just give an impression of how these help. So the neighborhood of squares in general is at most 10, and it's not regular 10 cones which give you this bound of 10, but you have to compute, and don't look at all these ugly numbers, just look at the drawing, and maybe there, because we have others. So it was worth investing in. There are no patterns there. So if you take a regular 10 cone, it's not yet good. It won't be good. But you can profit of the particular form of a square, which has some flat places and has some corners, and cheat a bit. So modify your regular 10 cone. It won't be regular anymore, but its vertices will still be on unit disk to apply this first lemma. And actually, the first lemma plus Thales will suffice. This more complicated third one will not have to be used. And this allows with the patches, but you will need the patches. Without the patches, actually, we could get down to 13, but not further. You can get the result that the tau of the neighborhood of squares is most 10. And then for the half cycle, I have just shown two patches there. Forget also about the computation, but you need to go to get a little wet with computations with that we did with Mathematica, and to fill in, and you need this triangle criterion. That's why. So these lemmas, these patches were found because of needs for estimating the number of neighbors. Okay, this is all, and I just summarized some questions that most of them were mentioned during the talk. So are there axis parallel squares with tau over nu at bigger than 3/2? Are there squares, not necessarily axis parallel, bigger than 3? The first case, small case that we cannot solve for Wegener, for rectangles, is nu equal 4. We don't know whether the optimum is 7 or 8, and nobody seems to know. So that's, and of course, that's just a very small concrete problem, but these were useful for getting the results. So this is how we proceeded, that we tried to understand them on these first cases that are open, and that's how we could get forward in general to get the results for dancing squares and of equal size and or not equal size. Tight, there are not really tight examples for Wegener, almost tight by Jelinek, which occurs in a paper of Chilean colleagues, Correa and his co-workers. But it's not exactly Wegener. It's a small constant less than Wegener. So somehow understanding really tight examples for Wegener could also help in understanding the problem better. And finally, for not necessarily unit squares with nu at most 3 is tau at most 4 true. This is the first case for squares, which is open for this 3/2 conjecture, if we would think that for squares, instead of the bound 2, the bound 3 half holds. Now, some big problems, new equal one case, as we saw, people care about it for disks, and nothing seems to be known for not necessarily axis parallel squares. So we don't know whether nu equal 1 implies tau at most 3 or it can be also 4. Well, the gaps, there are big differences between upper and lower bounds, like for the TSP, so they seem to be difficult to overcome. Tau, yeah, so nu, as we discussed it in the beginning, for nu there are 2 plus epsilon approximations, but for tau it seems to not to be any bound, or maybe they András and Fabrizio, maybe you know some constant bounds for tau, for the approximation ratio, for axis parallel rectangles.
Yeah, sure, that's the 2 plus epsilon that you mentioned on your previous slide, right? Or
That was for nu. That was for disjoint, but for minimum music set for.
okay, that's a completely different game.
Well, it's complete. It may be completely different. I hope it won't, because if you prove Wegener, then they will be related. So then you get at the same time the two. But what you had for nu, and so you say it's a different problem, and you don't know, and there doesn't seem to be results. So that's. But maybe your methods of separation and. So maybe they could work, it's not excluded. The hardness results are missing for the tensing general cases. You don't have the tau bound anymore. Here are these lines which are covered, every point is covered by at most 2 of them, but still tau is big. And nu is 1, right? So this is the case where nu is 1 and tau is n. And then some other quantities, so we shouldn't stick to tau and nu, but like yesterday, the question was raised for the TSP that you may have not only the linear relaxation, so you may have other quantities, maybe arising from linear programs, that replace for bounding tau, that replace nu, and for bounding nu, they replace tau, so who knows? Okay, these are the problems, yeah, this is the result for 2 with minus 2 plus epsilon. And this this mind the gap idea was András Gyárfás's idea when he worked on his conjectures. Then he said hello every day by saying mind the gap, because he saw it at the train stations in the US, in North America. So it's mind the gap. Sometimes it is big, like on the second picture. It goes until very far. And we should also watch the gap. So thank you for your attention.